Hello everyone, welcome to my channel Chemistry by ANR. This part of the session is on chemical reactions of amines. Now amines are having NH2 functional group if it is 1 degree. If I consider a primary, then it is NH2. Secondary, it will be bonded with 2 carbon atoms. Nitrogen is bonded directly with 2 carbon atoms. And for tertiary, nitrogen is bonded with 3 carbon atoms. Now, the first and the foremost property of amine is the basic nature on account of the presence of lone pair over nitrogen. Now, there are 2 things that bring out the chemical reactions of amines. One is the electronegativity difference between nitrogen and hydrogen, and the second is the presence of unshared pair of electron over the nitrogen atom. Now this unshared pair of electron over the nitrogen atom is the lone pair with which it is capable of abstracting an acidic proton. And this is the reaction that we are seeing, where if I say that this RNH2 is a base, then it is of course a Lewis base because it is having a lone pair, and Lewis bases are lone pair donors. We can also say, as per the protonic concept, that they are capable of abstracting proton. So nitrogen is capable of abstracting proton and HX is capable of donating proton, and so it is acidic in nature. So this is the salt that is obtained on account of the reaction between an acid with the base, which is the amine. It's basic in nature. So it forms salt. This example is of aliphatic amines, and the next example is of aromatic amine. So this is of aromatic amine. We can see the NH2 group is directly attached to the benzene ring, and so it is aromatic in nature. Now with this lone pair, it is capable of abstracting the acidic proton. This is the lone pair, and with this lone pair, it is capable of abstracting the proton. So it is like this, and there is a Cl minus coming out, and so this is NH3 plus and Cl minus. It is known as anilinium ion or anilinium chloride because of the counter ion Cl minus. Now aniline is acting as a base here because it is capable of abstracting proton. Now let us see the difference between the basic nature of aniline and basic nature of this aliphatic amine. Now I said the basic nature of amine is on account of the presence of the lone pair over the nitrogen atom. The presence of an alkyl group having plus I effect enhances the electron density over the nitrogen atom and hence gives greater basic nature. Now I said the presence of the alkyl group having plus I effect enhances the electron density over the nitrogen atom and hence is acting as a base. Now, if I talk about aniline, which is again basic in nature, but it is an aromatic amine. Now, here the nitrogen atom has a lone pair above it, which is engaged in resonance with the benzene ring, with the aromatic ring, because it is in conjugation. And on account of this is the plus R effect, which increases the electron density over the benzene ring. Now on account of this plus R effect, the electron density over the nitrogen atom shifts away from the nitrogen atom and moves towards the benzene ring. So I can say that the electron density over the nitrogen if it is an aliphatic amine, is greater than the electron density over the nitrogen atom if it is an aromatic amine. Now, amine salts, these are the amine salts. So, amine salts on reaction with base like NaOH or maybe KOH regenerates the parent amine. Why? The reason is this amine salt is now capable of donating H plus and acts as a conjugate acid. So if it donates H plus to OH minus, which acts as a conjugate base, now what happens is the H plus is abstracted by OH minus, forming H2O. And you obtain a neutral RNH2 molecule, which we can say is regenerated. Why regenerated? Because reaction of RNH2 with HX gives you the salt, which is RNH3 plus and X minus, and hence this reaction was a reversible reaction. You can reverse the reaction, that is, you can obtain the starting RNH2 by treating it with a base like NaOH. Amine salts are soluble in water. The reason is its polar nature, the positive and the negative ions, on account of which it obtains a polar nature, and hence it is soluble in water and insoluble in organic solvents like ethers. Thus, this reaction is the basis for the separation of amines from non-basic organic compounds insoluble in water. Why? Now, we have seen in our previous classes, class 10, class 9, that we can separate compounds based on their solubility effect. Suppose a compound is soluble in organic solvent and the other is soluble in polar solvents like water. So I can always use the solubility method to separate them. Thus, this is that part that is used to separate, say, amine salts, which is soluble in water, from any compound which is insoluble and is soluble in organic solvents, which is less polar. Now, reaction of amine with mineral acid to form the ammonium salt, we have just now seen. It depicts the basic nature of amine and can act as an evidence to prove that amines are basic in nature. And why amines were basic in nature? On account of the presence of lone pair or unshared pair of electrons over nitrogen atom, for which it was acting as a Lewis base. Lewis base are lone pair holders, or rather we can say lone pair donors are Lewis bases. Now, basic nature of amines can be understood in terms of Kb and pKb values. Just as in case of carboxylic acid, we had compared the acidity with respect to Ka and pKa. Here we are going to compare the basicity of amines with respect to Kb and pKb. So if the Kb value is greater, pKb value is less, because there is an inverse relation. Basicity of amines or maybe of any compound will then be considered to be greater. So greater the Kb value, lesser the pKb value, greater is the basicity of the compound, and greater is the tendency of the compound to donate its lone pair. So RNH2 with its lone pair abstracts the H of H2O and generates OH minus. So this is acid. H2O is acting RNH2 is base, H2O is acting as an acid here, and you obtain RNH3 plus, which is capable of donation of H plus, and so it is conjugate acid, and OH minus capable of abstraction of H plus, so it is conjugate base. Now, the system is in equilibrium, for which I can write K, which is the equilibrium constant, which is equal to the product of the molar concentration of the products divided by the product of the molar concentration of the reactants. That is what is shown here. Now remember that the molar concentration of H2O with respect to time does not change much and is considered to be a constant. This constant can be represented by Kb, and it is directly related to the molar concentration of OH minus ion. So if the Kb value is greater, that means more and more OH minus ion is obtained in the medium, which is the reason for the basicity. So pKb is equal to negative logarithm of Kb, hence for which pKb and Kb has inverse relation. So larger the value of Kb, smaller the value of pKb, stronger is the base. That is what we have seen just now. So here are some examples, pKb values, and just now we have said that if the pKb value is less, then only the basicity of the compound is greater. So I can say that 3.38 pKb value for methanamine is greater because it is having a lesser value, methanamine, than N-methyl methanamine, than N-dimethyl methanamine. But here it is in aqueous phase. So we have two cases of comparison of basicity of amines. One is the aqueous phase and the other is the gaseous phase. Now, in the gaseous phase, we don't have any other factor taking play or important. What is important is only the plus I effect of the alkyl groups attached to the nitrogen atom. And for that case, I can say that for any gas phase, if the number of alkyl group is greater, then the basicity will be greater. So for those cases, 3 degree will be greater than 2 degree, will be greater than 1 degree, will be greater than NH3 based on only plus I effect. And it occurs in a gas phase reaction, or rather gas phase comparison. But if we say it is aqueous phase, then the order is changing. Why is it changing? That we need to understand. Now, the discrepancy which is being seen over here based on the plus I and the minus I effects, that is not the only factor. The other factor besides inductive effect that affects the basicity of amines in aqueous solution are solvation effect, steric hindrance, and so if I say solvation effect, then I will say the capacity of forming hydrogen bonding with the solvent particles. Just let us think over it. Structure-based relationship of amines, that is based on the structure, how the basicity of amines are changing. It depends on basic character of these amines, actually depend on the ease of formation of the cation by accepting the proton from the acid. So I can say the ease of accepting a proton. Based on that, the basicity of amine will be judged, or rather I can say the stability of the cation. Why? The cation that is obtained is conjugate acid. So remember that more stable the conjugate acid is, greater is the basicity of the amine. So just like the stability of conjugate base is judged by I will say acid strength, or rather acid strength is judged by the stability of the conjugate base. Similarly, the basic strength is judged by the stability of the conjugate acid. Now, the conjugate acid which we had seen over here was having what? It was having a positive charge. So anything that increases the positive charge over the conjugate acid will be destabilizing the conjugate acid. And anything that decreases the positive charge over the conjugate acid will be stabilizing the conjugate acid. So let us explore the concept. So alkanamines versus ammonia. Alkanamine means amine which is substituted by alkanes, alkyl groups. So this is the alkyl group and it is alkanamine. That means it is alkanes but it is substituted. Okay, like if I say RNH2, in NH3 the H is substituted by alkyl group, then it is known as alkanamine. How it is different? Now R group has plus I effect. If it has plus I effect, it increases the electron density over the nitrogen atom, for which it is abstracting the acidic proton more efficiently than it will be occurring for NH3, where the 3 hydrogen atoms are bonded to nitrogen. So, due to the electron releasing tendency of the alkyl group, that is plus I effect, it adds on, increases electron density over nitrogen. Thus, it is more available for sharing with the proton. So, what happens is the substituted ammonium ion, this ammonium ion formed from the amine, is stabilized due to the dispersal of the positive charge by plus I effect of the alkyl group. Just now I said any factor that increases the positive charge causes destabilization, and that decreases the positive charge over nitrogen causes stabilization. This R group has plus I effect. It has plus I effect, for which the electron density over the nitrogen atom increases, and this is the conjugate acid, for which the base is more strong. Why? Because this conjugate acid is more stable on account of this alkyl group. So this alkyl group reduces the positive charge over nitrogen and hence increases the stability of the conjugate acid and hence increases the strength of the base. So alkyl amines are stronger bases than ammonia for this particular reason. Now, the basic nature of aliphatic amines should increase with increase in number of alkyl group. Why? Because if the number of alkyl group increases, then the number of groups having plus I effect is also increasing. This happens in the gaseous phase, which I have shown here. So for a gas phase, the order of basicity is this. Why? Because it is only inductive effect that is playing its role. And so a tertiary amine has greater basicity than 2 degree, then 1 degree, than NH3. The trend is not regular if you take aqueous solution or aqueous state. That is what is seen in the pKb values in table 9.3. What happens in aqueous phase? Why does the trend that is shown in the gaseous phase is reversed or somewhat reversed, not completely? Why it is so? Because if I say aqueous phase, that means the amine has interaction with the water molecules, which is known as the solvation effect. So solvation effect means the capacity of these amines to form hydrogen bond with the water molecules. To form hydrogen bond with the water molecules. That is known as solvation effect. Now, if it is a 1 degree, then this extent of hydrogen bonding with H2O molecule is maximum than in a 2 degree, than in a 3 degree amine in the aqueous phase. So I can say the extent of solvation order is this, and this is the decrease in solvation order. This is in decrease in solvation effect or order, or decrease in the order of the extent of hydrogen bonding. So greater the size of the ion, lesser will be the solvation and less stable will be the ion. Why? Because if the size of the ion or size of the alkyl group goes on increasing, greater hydrophobic part we are having. That means the non-polar part is increasing when I am moving from 1 degree to 2 degree to 3 degree, which hinders the formation of the hydrogen bonding with the water molecules. So greater is the stability of the substituted ammonium cation, greater should be the corresponding amine as a base. That means strength of the amine as a base. So the order of basicity for aliphatic amine is primary greater than secondary greater than tertiary on the basis of what? On the basis of solvation, on the basis of solvation effect, which was observed to be opposite to that of inductive effect. So based on inductive effect, based on plus I effect, I will say a 3 degree has greater basicity than 2 degree, than 1 degree, than NH3 of course. But based on solvation effect, it is 1 degree greater than 2 degree greater than 3 degree of course. Now, if I say the alkyl group, size of the alkyl group is small, that means CH3, then the steric hindrance to hydrogen bonding is less. No steric hindrance to hydrogen bonding, rather I will say less steric hindrance to hydrogen bonding if it is a methyl group. So if the alkyl group is methyl, then the steric hindrance is less. Steric hindrance what? Steric hindrance to hydrogen bonding is less. So size of the alkyl group is another factor. Therefore, the change of nature of the alkyl group from say a methyl to ethyl affects the order of the basic strength, because if the size of the alkyl group is increasing, then the hydrogen bonding is becoming weaker. So, for that case, for formation of hydrogen bonding, we will say that a 3 degree will make it weak. So for that case, based on steric hindrance to hydrogen bonding or based on the hydrogen bonding affected by the R group, we can say that the order is 1 degree greater than 2 degree greater than 3 degree. Why? Because in a 3 degree, the number of alkyl group is greater, which produces greater steric hindrance to hydrogen bonding, and thus the basicity is weak. Now, if I compare the three effects, the inductive effect, solvation effect, the hydrogen bonding, we can see that the position of a 2-degree amine remains the same in aqueous phase, of course. Now, combining effect or combined effect of these will give a 2-degree greater basicity than a 1-degree than a 3-degree. The reason is in this three effects, 1-degree is having greater basicity or greater effect in two of the factors. So when you compare the three factors, it is 2-degree greater than 1-degree than 3-degree. But the case is different for ethyl and methyl. So here we are seeing that for a smaller alkyl group, it is a 2-degree greater than 1-degree greater than 3-degree than NH3. If we consider it to be methyl, of course, in aqueous phase, we are comparing the basicity. But if not methyl, if ethyl or maybe a bulky R group, then it is a 2-degree greater than 3-degree greater than 1-degree greater than NH3. Why? The reason is the plus I effect becomes more powerful in this case, increasing the electron density over the nitrogen atom, which is more powerful. So here we can see that if we change from CH3 to C2H5, there is a change because of the inductive effect. That is, there is a subtle interplay of inductive effect, solvation effect, and steric hindrance of the alkyl group that decides the basic strength of alkyl amines in aqueous solution. And these two orders will actually give you a proper example to remember how, with the change in the bulk factor of the alkyl group, the basic character, the basic order changes in aqueous phase. Next comes the comparison of aryl amines with ammonia, where I already have mentioned that aryl amines are less basic on account of plus R effect, where the electron density moves away from the nitrogen atom towards the benzene ring. Thus, the pKb value of aniline is quite high. Why is it so? Because it is less basic in nature. And why is it less basic? Because of the plus R effect that reduces or decreases the electron density over the nitrogen atom, in aniline. And so it results in the decrease in the basic nature. But that doesn't mean that aniline will not get protonated. Aniline gets protonated, but maybe the lone pair is less available for protonation. The anilinium ion that is obtained by accepting a proton has two resonating forms. These are the resonating forms, which are the Kekulé structure of benzene. If you minutely notice, it is only the ring resonance that is happening here. So we know greater the number of resonating structures, greater is the stability. So you can say that aniline has 5 resonating structures and is more stable than the anilinium ion, which is having 2 resonating forms. So we can say that the proton accepting capacity or the basic nature of aniline or any other aromatic amine will be less than that of ammonia. So that is how we can compare the basic nature of amines, which depends on the phase, whether it is gaseous phase or it is aqueous phase. And If it is aqueous phase, it of course depends on whether it has a methyl group or it has an ethyl group, that is the bulk factor of the alkyl group. And we can also compare the basic strength of aromatic amines or arylamines with ammonia based on the availability of the electron density or the lone pair over the nitrogen atom. In case of substituted aniline, where we have electron releasing groups means electron donating group, what happens? It increases the basic strength because presence of electron donating group increases the electron density over the nitrogen atom in arylamines, for which the I will say basicity is greater and the stability of the conjugate acid is also greater because of the presence of the electron donating group, which reduces the positive charge over nitrogen atom in the conjugate acid, giving it more stability. On the other hand, presence of electron withdrawing group will actually decrease the basic strength of the arylamines on account of the decrease in the electron density over the nitrogen atom. And such electron withdrawing groups are NO2, SO3H, COOH, X, all these atoms or groups of atoms that have the capacity of taking away electron density from the benzene ring, maybe on account of minus I or maybe on account of minus R effect. So, this is an example question where we can see arrange the following in decreasing order of basic strength. This is aniline, aromatic amine. This is ethylamine. Now, ethylamine and aniline both are 1 degree. Only the difference is one is aliphatic, the other is aromatic. This is a 2 degree amine and the other is ammonia. So here we can see that aromatic amines have the minimum basic strength because of the less availability of the lone pair or electron density over nitrogen atom, and here the inductive effect is more powerful, hence it increases the electron density over the nitrogen atom. Nothing is said about the medium, so you can assume it or in general based on the inductive effect. Next, alkylation of amines is a part of the unit which we have done in unit 6, alkylation reaction over amines, and here we will see acylation. Acylation, acyl group is RCO group, or here we can see that this RCO group, the COR is coming to the structure by replacing one of the hydrogen of amine. So this reaction takes place with aliphatic as well as aromatic primary and secondary amines, which reacts with acyl chlorides or acid chloride, anhydrides and esters by the method of nucleophilic substitution reaction, where here we can see that the amine is a nucleophile which has a lone pair above, and here this carbon is the delta positive carbon having greater electrophilic nature on account of the polarity of C double bonded O. So the nitrogen having its lone pair attacks the electrophilic site, that is the delta positive site, and there is oxygen getting O minus. It can return and eliminate Cl minus. So we can assume that there is ultimate elimination of HCl, and hence this reaction is catalyzed by organic base like pyridine, which removes pyridine assist in removal of HCl and hence drives the reaction forward or shifts the equilibrium towards the right hand side. So this was the example with acid chloride. This is the example with acid anhydride. The same thing I will say, this COR comes in place of H and you get this where there is elimination of rest of the part, which is CH3COO and H forming CH3COOH here. Now the next reaction is a benzoylation reaction. Whether we will have a benzoyl group or an acyl group, it depends on what type of reagent you are taking. If you take benzoyl chloride, then the group that will be coming is COC6H5 by eliminating one of the H, or rather by substituting one of the H, and the side product is again HCl. So the reaction will be catalyzed or the reaction rate will increase in presence of pyridine, which is organic base. Now coming on to the carbylamine reaction, which is a name reaction. Carbylamine reaction is a name reaction and it is a distinguishing test for aliphatic and aromatic primary amines. So it is used as a distinguishing test for aliphatic and aromatic primary amines, which on heating with chloroform CHCl3 and alcoholic potassium hydroxide forms isocyanides, which have obnoxious smell. This term obnoxious means offensive smell. Now secondary and tertiary amine will not show this reaction, for which this reaction can be used as a distinguishing test for aliphatic and aromatic primary amines. So this is a very important reaction. Next is the reaction with nitrous acid, which is HNO2. Now nitrous acid is not available in the lab as it is. It needs to be prepared in situ by the reaction of mineral acid and sodium nitrite. So mineral acid like HCl and sodium nitrite NaNO2. Now this reaction is known as diazotization reaction. It is known as diazotization reaction or the reaction to form diazonium salt. If we start with aliphatic primary amine, we will get aliphatic diazonium salt. If we start with aromatic amine, we will get aromatic diazonium salt or benzene diazonium salt. Point to be noted is aliphatic diazonium salts are unstable in nature, and so this square bracket is given to show that it is an unstable intermediate which breaks down, undergoes hydrolysis and evolves nitrogen gas and finally gives you alcohol as the product. The final product with aliphatic primary amines will be alcohol and not the diazonium chloride or the diazonium salt, because it is unstable in nature. It is unstable in nature. Whereas the benzene diazonium chloride is resonance stabilized. On account of resonance, it is having greater stability, and so it is an important intermediate for various organic synthesis. You can prepare a wide variety of organic compounds from this benzene diazonium chloride. It is an important intermediate. So next is reaction with aryl sulfonyl chloride, which is termed as Hinsberg reagent. Hinsberg reagent is also used as a distinguishing test for types of amines. Like Lucas reagent was used for distinguishing test for types of alcohols. Hinsberg reagent is used to distinguish a 1 degree, 2 degree or 3 degree amine. And how the reaction proceeds. If I start with a primary amine, say this is an example of primary amine on account of the reaction with Hinsberg reagent. And what is Hinsberg reagent? It is benzene sulfonyl chloride. Because of the presence of the sulfonyl group present in the compound, what happens? The H and Cl gets eliminated and you get HCl as the side product, and this is the product which is obtained having an acidic H over here. It has an acidic H. We can see this is an acidic H. Why it is acidic H? On account of the presence of two double bonded O with sulfur. It has the electron pulling or attracting tendency, for which this H becomes acidic in nature, and so it is soluble in alkali. This can happen when you take 1 degree or primary amine. Now the product for a secondary amine after the elimination of HCl due to absence of any acidic hydrogen, this product is insoluble in alkali. So this is insoluble in alkali. And so it doesn't mean that with Hinsberg reagent, a 2 degree amine will not react. It reacts, but the product is insoluble in alkali due to the absence of acidic hydrogen. A 3 degree amine does not contain the H, and so it will not react at all. So tertiary amines do not react with the Hinsberg reagent, and so this can be used as a distinguishing test. So how it can be used? For a 1 degree aliphatic or aromatic amine, the product is soluble in alkali. For 2 degree amines, the product is insoluble in alkali, and for 3 degree amine, the product is not formed at all. So the next important reaction is the electrophilic substitution. Electrophilic substitution of aromatic amines. Why? Because aniline we can see has what? Plus R effect, because the lone pair goes into resonance and so increases the electron density over the benzene ring or the aromatic ring. And it obtains a negative charge selectively over the ortho positions and para position on account of resonance. So if there is electrophilic substitution occurring, it will occur at the ortho or para position or both. So ortho-para positions of NH2 group gets the product formation, and if I use a more polar medium like say bromine water, which is a very reactive reagent, even at room temperature, it gives a white precipitate. So a white PPT is obtained by reacting aniline with bromine water, but keep in mind that the ortho and the para positions should be free and should not be substituted in order to obtain this product. It's a tri-substituted product. So it can be used as a distinguishing test for aniline, but not for any substituted aniline, especially in the ortho and the para positions. Now here the main problem with this electrophilic substitution is the very high reactivity of aromatic amines, for which you don't get a mono-substituted product. You get a tendency to obtain a multi-substituted product. More than one position gets substituted or activated. So you need a reaction that can reduce the activation of aniline and deactivate it to some extent. And the reaction is acetylation reaction. By the method of acetylation, bringing an acetyl group in place of H actually reduces what? The activity over the benzene ring due to external conjugation. See, this lone pair is now into external conjugation and the electron density in the benzene ring is somewhat reduced. I will not say the electron density in the benzene ring is not there, but it is somewhat reduced on account of external conjugation. That is, outside the benzene ring, the electron density is reduced and it moves away from the benzene ring to some extent. So this is known as a blocking method. And by blocking the NH2 group by acetylation, you can reduce the activity. And now you carry out whatever reaction you want to and finally obtain the aniline back by hydrolysis method, where it will break the bond and give you this product. You will get NH2 back. So this is the external conjugation that I was talking about. So if we carry out nitration, the direct nitration of aniline actually gives terry-oxidation products, that is, in addition to the ortho and the para, this is the ortho, this is the para, you get considerable amount of the meta product. See, the amount of the meta product is even greater than the ortho product. The yield is greater, it's considerable. Why is it so? Because in this acidic medium, aniline is basic in nature, there is proton abstraction and it forms anilinium ion. And finally, this anilinium ion which you are getting is NH3 plus. On account of the plus charge over nitrogen, there occurs minus R effect and hence deactivation of the benzene ring, for which you get the meta substituted product as a good yield. So, this is the reason for the meta product. Now, if I don't want this terry-oxidation product, a mixture of product, and I just want a para product to be the major product, what I need to do is, first I need to protect the NH2 group, or I can say I need to block or I need to deactivate or less activate the NH2 group by acetylation method in presence of pyridine in order to remove the HCl that is formed, or here in order to remove the acetic acid that is obtained in order to increase the rate of the reaction. After you obtain acetanilide, which is obtained by acetylation method over aniline, you can carry out nitration. This is the nitration that is carried out, and you know that the ortho position is having greater steric hindrance, on account of which the para product is the major product. And after that, you have to hydrolyze and you need to obtain this NH2 back in order to obtain para-nitroaniline as the major product. So next, you have sulfonation reaction, wherein we can see the sulfonic acid group SO3H group to come in the para position. How? By reacting aniline with concentrated sulfuric acid, you get anilinium hydrogen sulfate. Why? The reason is the H plus abstraction. So we can say sulfuric acid has this type of structure, right? It has this type of structure. So this lone pair abstracts the proton and you get NH3 plus and the counter ion is HSO4 minus. So this is anilinium hydrogen sulfate. And at a temperature 453 to 473 Kelvin, it gives you para-amino benzene sulfonic acid, which is known as sulfonilic acid, the common name. This sulfonilic acid has a basic functional group and an acidic functional group together. And so this is amphoteric in nature. Since it is amphoteric in nature, the acidic functional group SO3H can actually give its proton to this NH2 and NH2 becomes NH3 plus and SO3H becomes SO3 minus. So this dipolar ion, that is a compound containing both positive and negative charges in it, is known as Zwitter ion, which is obtained from this sulfonilic acid and it is in equilibrium with this form. So both the forms coexist. Another important fact is aniline does not undergo Friedel-Crafts reaction. Like benzoic acid we have seen. Similarly, but what is the reason over here? Here we can see neither alkylation nor acetylation reaction is feasible with aniline due to the salt formation with the Lewis acid catalyst aluminium chloride. Why? Because aniline is a base and the aluminium chloride is a Lewis acid. Thus, it results in a salt formation. So, remember that this aluminium chloride after the salt formation gives nitrogen a positive charge and hence deactivates it towards Friedel-Crafts reaction. So, aniline does not give Friedel-Crafts reaction. These are the in-text questions 4, 5, 6, 7, 8, which you can see the solution here. It is given over here. See, arrange the following in increasing order of their basic strength. See over here, aromatic minimum, then NH3, then you are having 1 degree. This is again 1 degree, but what is the difference? Here you have a greater hydrophobic part and here the hydrophobic part is less and this is a 2 degree. This is a 2 degree. No phase is said over here. Okay. So next again, aromatic 1 degree, 3 degree, 2 degree. So 2 degree is having maximum, then 3 degree, then 1 degree, then aromatic over here. So for all the cases, you keep in mind why 2 degree is greater. The reason is it is ethyl, not methyl. Had it been methyl, the third case, the order would have changed. See over here what is happening. Again here the order is for a methyl. The inductive effect is less, right? So here a 2 degree, 1 degree, 3 degree and here hydrophobic part is more. So it is again a 1 degree and this is aromatic. Next, complete the following acid-base reaction. Just it will abstract the proton and it will form a salt like this. Next, write the reactions of the final alkylation product of aniline with excess of methyl iodide. Now, this is the alkylation reaction. This is acting as a nucleophile and delta positive character over alkyl group. So, it is a nucleophilic attack and this is the product that you are obtaining. So here we can see finally in this what happens is one of the H is substituted by the alkyl group and the other is remaining. Because the question is what will happen in presence of sodium carbonate? So obviously this is a reaction where sodium carbonate will generate CO2 gas. Again, the same thing will happen over here. Then here a CH3I is used. Already a CH3 is there. So substituting one H, this H by another this CH3, and you get CH3 whole twice. And finally with sodium carbonate, a carbonate ion is obtained. Now this, write the chemical reaction of aniline with benzoyl chloride, which is Hinsberg reagent, and this is having 1 degree, so it is having what? Finally it is having one acidic H. Okay, no, this is benzoyl chloride, so it is not Hinsberg reagent, it is benzoyl chloride, means benzylation. I rectify it, it is benzylation reaction, not Hinsberg reagent, right? So in benzylation, what happens? 1H is substituted by the benzoyl group, that is COC6H5. And write structures of different isomers of this. This you can try on your own one by one. Okay, and name them with respect to IUPAC norms and see which will liberate the nitrogen gas. Okay, so which will liberate the nitrogen gas? It depends on aliphatic 1 degree amine, which can liberate the nitrogen gas. So I hope this concept was quite clear to you. It will be more clear to you if you go through the NCERT book along with the video and understand the concepts, jot down the important points. So see you in the next video. Till then, bye all of you.